Morning. I think we've had a wonderful time celebrating a 25th anniversary. We are still celebrating it, and it's good we see this already. I also thank you for celebrating a 50th birthday, except you still have to learn how to sing a birthday song. That didn't quite work out. And now we have to think further about bigger numbers. And the next thing to celebrate is the 70th birthday. And I want to make a brief announcement here. So, there is a conference in honor of John Hubbard's 70th birthday, taking place in Bremen in August. You see it here. And I would like to invite all of you, and I hope you're coming. And we try our best to make it at least almost as good as this wonderful event here. Thank you.
Right, so I have the pleasure to introduce Carsten. We will speak about quasi-conformal incompatibility of satellite copies of the Mandelbrot set.
Thank you very much. I'd like to join my colleagues in thanking the organizers for a beautiful conference and for inviting me here to give a talk. My first visit to Stony Brook was in June 1991, so that brings me into the class of 24. What I'm going to talk to you about is joint work with a former student of mine, Luna Luminaco. So joint with. And it's going to be about the signature dual, as Yair was calling it. So let me see if I can give you one which looks almost as beautiful as he did. In fact, what it's going to be about is the deep fjords of this signature dual, rather than the floating islands out in the deep sea. So here we think of this as the connectedness locus of the quadratic polynomials q sub c of c equal to z squared plus c. And just to make it different, there's another signature dual which is almost as known, which looks a little bit like this. I suppose there should be an extra one. And which is the connectedness locus of another normalization, the fixed point normalization of quadratic polynomial, so p sub lambda of z equal to lambda z plus z squared. And as many of you may know, there's a relation, a simple relation between c and lambda. So c of lambda is lambda over 2 minus lambda squared over 4. So to tell the story that I want to tell, I should recall you the notion of polynomial-like maps. Of course, it entered at least in Jeremy's talk. But let me just recall that a polynomial-like map is a homeomorphic map between topological disks, U prime contained, compactly contained in U. So F, a proper map from U prime to U of degree D bigger than 2, or bigger than or equal to 2, which has, well, such a map has a filled Julia set, KF, and a Julia set, so KF, filled Julia set, and Julia set, which is the boundary of KF. So such objects were, of course, introduced by Douady and Hubbard, and they proved the straightening theorem, which asserts that if I have a polynomial-like map, F, then there exists, so given F, from U prime to U, there exists a polynomial P, degree P equal to D, there exists a quasi-conformal homeomorphism phi from some domain V, a subset of U, into C, such that if you have F onto V, say the preimage is V prime, and you apply phi, you obtain the polynomial P on the image. And moreover, if Kf connected, it implies that P is unique up to affine conjugacy. Just write up to affine here. So for quadratic polynomials, each C represents the unique affine conjugacy class, which has a critical point at 0. So it means that if I have F, so if degree of F is 2, and Kf connected, I get a map, the P is of the form Q sub C for some C. Now if I have a parametrized family, so suppose I have some space W, giving me sets U sub W, U prime sub W, U sub W, and quadratic polynomial-like maps F of degree 2, depending holomorphically on W, say, I get a map from what we could call the connectedness locus in W into the Mandelbrot set. And if my family has a specific property, let's say that it's full and simple, so if I make a little tour in my parameter disk and I assume that then the critical value make one tour around the critical point, then in fact I know that inside here I have another little copy of our doodle, the Mandelbrot set here. This of course appeared in Jeremy's talk, where we saw that there were lots of these little things sitting out here somewhere. There are lots of other places where you find these. In fact, you will find a copy sitting here, and maybe you need a little bit of more fantasy to see that this here should be a copy of the Mandelbrot set. So let me help your imagination a little bit. Before that, let me just say that so we have this map chi given by straightening from let's call it M prime, the connectedness locus of our family, onto M. And before I go to these satellite ones, let me just say that, so Douady and Hubbard showed that these were our homeomorphisms, and this was improved by Lyubich. So Lyubich, let me write implied, that key is in fact a QC homeo. So all these little doodles, free-floating primitive ones out here, are actually quasi-conformal copies of the actual Mandelbrot set. So let me get to the satellite ones. So for instance, let me take a center like this, or actually, I'm so used to drawing the upper one, and this is what I'm going to do. So you get a Julia set that looks a little bit like this. So you have the critical point, which maps to the critical value to its second iterate and maybe comes back here. Then we have a fixed point, which has a pre-image, which has a second pre-image, which has a second pre-image, etc. But you have pre-images of this here, and which in turn has a pre-image here. To get a quadratic-like map, what you do is you take a disk, say a big disk like this. There's a way to construct that so that under the Q iterate, it has a pre-image compactly contained in itself. So your polynomial, either Q sub C or P lambda, depending which one you take, maps the smaller disk to the larger disk. Let me just do with a color here. And of course, it should cut through the ears when you take pre-images. So it turns out that when we move, it's so far up I can hardly touch to the right one, we can actually deform our parameter and find almost a full family like this, sitting with its roots on the unit circle. So let me point to, it's difficult. Okay. Pardon?
Missing one? The
S. Yeah. Okay, I understand the curve. Well, I mean, in some sense, the S is there. So it's true that when you look at it, say, let's take this one here. The S is actually there, but it's been straightened, so there's no cusp. It's round. And it turns out also that you cannot do this renormalization picture here for the parameter that corresponds to the prick in the S. But so what's the problem? So let's do a parameter which is sort of near the root. So what's going on is that your ears are growing fatter. You still have your critical orbit, but it doesn't come back to itself. It comes closer. And in fact, before you had a period free cycle, which has now been deliberated from its coalescence with the critical orbit, and is now very close to the fixed point in the middle here. So when you want to try and create a polynomial-like map, you have some restrictions. So your domain, or the range, has to avoid these two additional fixed points of the Q iterate. So you see you're having a pinching at this point, and going to the limit or taking the root, this Q cycle is going to coalesce on the fixed point, and there's no room. I mean, you have the pinching of the fundamental annulus, so there's no hope to have, in that case, a usual renormalization. And for exactly this reason, you cannot prove that, you can prove that even in this case there is a copy. It should be possible to get that down. So one here, say, which stretches out somewhere. And which, of course, has decorations from the original Mandelbrot set, but it's strictly smaller. And what I'm saying is that this root point doesn't have a renormalization as a polynomial-like map. And so you have this copy. You can actually prove, and the proof was completed by Hasinski, that it's a homeomorphic copy of the Mandelbrot set. But, and you can also prove, and this follows from this theory of Lyubich, that if you take away any little neighborhood of the root, then this natural homeomorphism onto the Mandelbrot set is actually a quasi-conformal homeomorphism.
And you can prove also that it cannot be better, that it cannot extend the quasi-conformality.
So that's the question.
No, but I mean the R's is like, I mean, you know, it's not a quasi-circle. Right?
So it's clear that here you don't have a cusp. So, I mean, from the point of view of quasi-conformal theory, you cannot straighten the cusp. So you cannot make this quasi-conformally onto this.
Yeah, that's what I think.
But maybe if you look at this picture here, so this is actually a double covering. And here I have conformally straightened the cusp. So why should it quasi-conform? I mean, maybe, so there's a way to think of this to say that, well, this half actually maps 1-to-1 onto the Mandelbrot set homeomorphically. And you can think that now here, so just as we have here, let's call it the 1/3 limb. So it's the unit disk. I have a boundary point here, which is the third root of unity. I have attached to this a little copy. Let's call that M1/3. If I go along the to argument 1/2, I have a little copy. Let's call that M1/2, etc. Then it would be natural to say, well, why don't you think of this as M001? Okay? And just think of this as a new limb we created for the Mandelbrot set. And you see we straighten the cusp, so maybe this copy here, which of course doesn't have any decorations, is quasi-conformally homeomorphic to a copy here and this, and why not? So this is a question. Are these ones quasi-conformally homomorphic to this? If not, are they quasi-conformally homomorphic to each other? What is the model? Let me put that. So are the satellite copies MPQ mutually QC equivalent? In the sense that this natural map that's defined using the dynamics, the straightening, gives you a map, and you can ask, is that map quasi-conformal? So how did this question come up? If you go back, there's a paper by Fagelia and Branner and Fagelia, where they prove that if you take two different limbs with the same denominator, then there's a homeomorphism, not just of the little copy, it's just the Douady Hubbard homeomorphism, but of the full limbs. And I know that Branner and decorations, everything you can, okay. And Lyubich and Branner was working for a long time, and probably still are, trying to prove that this homeomorphism is actually quasi-conformal. So Luna was visiting here in the autumn of 13 and was discussing with Misha and nice problem, and she has this notion of parabolic-like maps, which is a way to actually do a renormalization of this. So in this case, we had a parabolic fixed point. So her notion of parabolic-like maps can be described somewhat as follows. So take a disk. Don't care about what's really going on down here. The only thing we care about is that the pre-image should map properly by degree 2 onto the larger disk. And then, so you have this pair of rays actually coming in. So this is part of the theory of polynomial-like maps, which are invariant under the Q iterate, and which cuts out a part of the dynamics, where the dynamic is, well, it's not repelling, but it's univalent. And there's points here, the only way they can get back into the dynamical system is by escaping first.
So can you
Sure, a lot bigger.
Yes, I will try to do a caricature. Okay.
Big 6 inch.
So let's just do it very thick. So you have the critical point here, the critical value, its image. Let's just make a disk.
Writing a lot bigger.
Is that? Can you see the green?
Final one.
Yeah, I mean here, yeah.
Okay.
Giant sized.
Giant size. So here's your disk. Okay. Here's your parabolic fixed point. Here you have the body of your rabbit. It has a critical point down to here somewhere. There's a critical value. There's the image of the critical value sitting out here somewhere. You have the ear coming out here, which is nice and which has a pre-image sitting under the cube iterate. You have an ear going out here. And now you look at the pre-image of such a disk. Then, well, here, I mean, you have that repelling dynamics on the rays. So it sort of starts out nicely. It does something up here. It comes to the ray. But then, I mean, it's an attracting petal you have here. So certainly it's going to come out. Then you have a ray in this fjord also. So it's going to move inside here, but then it's coming out like this. So what I'm saying is, if you take the ray here and the ray here, well, this was the body, okay. The part of the dynamics which is sitting beneath the rays, it's univalent dynamics. And it doesn't come back into the dynamical system up here, so it doesn't really contribute to entropy. So we don't care about it. It can be whatever it wants. So we just focus on what is on the other side, as long as this is univalent. So that's the philosophy. And it turns out that if you have two objects of this kind, then they actually have quasi-conformally conjugate dynamics. So if I take two different limbs, or even this one here, which is sort of a fake limb, if I take the corresponding root parameters, do the parabolic-like renormalizations, then they're quasi-conformally conjugate. So they're not that much different. So, I mean, sort of the idea was that this should help in proving that limbs, or maybe just the copies, are quasi-conformally conjugate, or quasi-conformally equivalent. It sort of came as a surprise that they're not. So if you take two different denominators, do you like the picture? Ah, sorry. So given P over Q, P prime over Q prime, irreducible prime, thank you, irreducible rationals, with Q different from Q prime, you take, well, you have M PQ, you have M prime over Q prime, you have the Douady Hubbard homeomorphisms to the Mandelbrot set, and this gives you an induced homeomorphism between the copies. Then this zeta is not quasi-conformal in any neighborhood of the root. Then zeta is not QC in any neighborhood of roots.
What about away from?
Away from the root, if you cut out a little neighborhood of the root, then it follows from this Banach space structure on the space of polynomial-like maps that Lyubich has constructed, that actually the map is nice quasi-conformally outside. So it has apparently a dilatation that becomes worse and worse when you go into the root. My guess is that this map is actually conformal at the point. I mean, you can make a complex derivative, but the map is not quasi-conformal, so it has distortions on smaller scales that you don't see when you just compare at the point. Yes?
Why do you think it's conformal?
I'll come to that at the end of my talk, okay? So how can we try and understand what's going on? So if you fix P over Q for the moment, let's denote by F lambda the restriction of P to the Q as a polynomial-like map, so from some U lambda to U lambda. Now I'm in this fixed point normalization, so the fixed point, which is parabolic at the root, has multiplier lambda to the power Q. So let's define capital lambda to be the principal logarithm of lambda to the power Q. So this defines me a map from the little copy into C, which sends the root to 0, and which sends my limb into the right half plane. And then, of course, the first question you may ask is it really a map on the little copy? Is it injective or something? Well, Yoko's inequality, that I'm not going to go too much into, implies that this set here is actually contained in a round disk of center log 2 and radius log 2. And log 2 is less than pi, so it's in a domain of univalence for log. Okay? So we might as well be working with this set. So call this lambda of MPQ and denote it by MPQ hat. Just for this. And then let's take another one, a P prime over Q prime. And not to mix up and make heavy notation, let's make the parameter mu. So G mu of Z is mu, well, it's P mu iterated Q prime times from some domain V mu prime to V mu, quadratic like. You do the same. So you put M equal to log of mu to the power Q prime. And you get the image in this log plane of your limb. So if, maybe this one is from the 1/2, and this one would be from the 1/3. So you'll see just like this. And let's call M hat P prime over Q prime the image M of MPQ. And then the induced homeomorphism zeta hat between MPQ hat and P prime Q prime hat. Okay, so I'm just lifting it to this log, and it's good parameters because they're univalent. You might ask, so why is this interesting? There are certain things that if you're old enough, and I'm barely old enough, there's some result from the 80s by Sullivan and Schub, which has an instance which has the following. So theorem. Let lambda be in MPQ hat. Let M equal to zeta hat of MPQ M prime Q prime hat. So these are the log multipliers of the quadratic like restrictions. Okay? So of course I could have put in here, I could have taken lambda, a lambda in MPQ, a mu in MPQ. But the statement is that if I have this, then the Douady Hubbard homeomorphism between the two copies is so that the two maps f lambda and f mu, well, f lambda g mu, are actually QC conjugate. Well, yeah, okay. So if there's no index on an M here, it's a Roman mu. Okay. Okay. Yeah. It's not a Mandelbrot set. I'm sorry.
Is the map going that way? Is psi hat going that way, or is it the other way?
What is?
It goes from the unprimed to primed on that word, unless.
No, the primes are on the right.
Yes. So why are you applying it here to something with the primes on it already?
Oh, I didn't. I hope I didn't.
Maybe this is chalk marks already on the board.
So lambda in M, there's no primes here, and there are primes here.
Just look at the formula. Psi hat of M hat sub P prime over Q prime.
Thank you.
Okay.
Thank you. Lambda. Yeah, that's good. Okay. So I take a lambda, which gives me an F lambda. It's QC conjugate to an unique G mu. So it's the one for which M is zeta hat of lambda. Okay? And I know that I have a conjugacy, QC, which is actually conformal on the filled Julia sets, but I'm not going to use that. And we actually have a lower bound on the dilatation of this conjugacy. So the statement is that if you look at Lehm soup for C going to 0 of log of the real dilatation of phi at Z, then this is at least the hyperbolic distance in the right half plane between lambda and M. So it's bigger than or equal to the hyperbolic distance in, say, H plus between lambda and M. So I don't know how many years old enough to remember such a theorem. I know that Mitsu is, because he told me that this is actually comes from Sullivan and Shoup. So how do you prove a thing like this? It's actually very elementary. So you have these two polynomial-like maps. Let me just draw them like this. They have a fixed point, 0, which is actually the unique fixed point which is fixed accessible. So it corresponds to the one with the fixed ray. We know here that we have Q rays in our case on one side, which are all homotopic relative to the Julia set, and which are fixed for the Q iterate. I have another one for Q prime. I have Q prime rays, also fixed. And I have a conjugacy, let's say I restrict it so that I have a conjugacy from with domain which is the outer to the outer. Now, if I look at the quotient torus made by puncturing a small disk around 0, and I look at the image of one of these curves, it suffices to take one of them. Say I take one here. Then this defines me a closed loop. If I take a little circle going around, say clockwise, it defines me another loop. So it defines me actually a point in Teichmüller space for a torus. Because I have a torus with two marked curves that generate the fundamental group. So it gives me a choice of logarithm of the multiplier. So it actually gives me a choice. And it turns out that this choice is exactly lambda in this case. So I have here one generator, lambda, and minus I 2 pi as the other one, and I have the usual picture of an elliptic curve. I have the same picture over here. So I have a quotient torus. I have an invariant arc that projects to a closed loop. I have the loop coming from going around that gives me a loop like this. It gives me another grid. It gives me actually M. And the reason why it's M is, well, you easily check that it comes from a way of viewing lambda and M is that there's another way of producing this picture. You can take the linearizer of this fixed point. You can precompose it with the exponential map, so you get a log linearizer. Then you can lift these external rays to this log linearizer, so they become curves which are actually invariant under a unique translation by unique logarithm of the multiplier, and the multiplier is this lambda to the power q. And that unique logarithm is actually lambda here, okay?
Is this picture... I would have expected a ray like this not to close up. I would have expected that you'd need all your rays.
It's because I'm taking the Q iterate. So I had a Q cycle.
You're already drawing.
Yeah. So this is F lambda. So this I have this. Okay, I should have put here an F lambda. I have here a G mu. So these are the renormalizations.
So in particular, these tori are quite different because the original multipliers were quite different.
Yeah. Certainly.
And you've raised them to different powers.
Yes, I raised them to different powers. Okay? If I have a conjugacy phi between them, it induces a quasi-conformal homeomorphism between the two marked tori, and it must map the homotopy type of the circle to the circle, the homotopic type of the projection of the blue curve to the homotopy type of the blue curve over here. So then by the Teichmüller Extremal Theorem, the dilatation of this quasi-conformal map between the tori has a dilatation which is at least, well, log of which is at least the hyperbolic distance between the two. And this is what I have up here. And then bringing it back to the dynamical plane, it means that no matter how close you go to this fixed point, 0, you will encounter places where the dilatation is at least, well, log of the dilatation is at least the hyperbolic distance between lambda and M. Okay? So this raises a natural question, which is, so I have this map. Is this a quasi-isometry? I mean, does it move points a bounded distance? That's a question. In the hyperbolic metric on the right half plane. So question. Does theta hat, does there exist a C such that, well, it depends, of course, on P over Q and P prime over Q prime, such that for lambda in MPQ hat, the hyperbolic distance between lambda and zeta of lambda is smaller than m.
Or is it called M?
C, thank you. Yeah, there are too many m's. Okay. So if you play a little bit with the proof of the Theis-Müller-Extremal theorem, and you play a little bit with holomorphic motions and using them to transfer information from dynamical space to parameter space, then if I pick a parameter lambda star, which is a Miserovich parameter, such that the critical value is prefixed to 0, my C hat has a similar lower bound on its dilatation near that point. So can I write here if I push the blackboard up afterwards?
Are you just introducing this critical orbit condition now? In this sentence, this is the first I noticed it. You're specializing now in that case?
Yes, well, I mean, yeah, to pass the parameter space, I need a place where I can actually witness this dilatation that I necessarily have in dynamical space. And I don't know, maybe Misha would not be able to do that everywhere, but at least we were only able to reproduce this near these special Miserovich parameters, which are like the dyadic tips of the little Mandelbrot.
So you're using this theorem of Conley, for example, about the correspondence of the...
It's similar, but we don't know how to use that theorem. So theorem, suppose lambda star in MPQ hat is a Miserovich parameter such that the critical value which is minus lambda star over 2 squared is prefixed to 0. Pardon?
In previous talk, they defined the Miserovich in a different way.
Yeah. This is restricted. This is Miserovich in the sense of Douady and Hubbard. Yes. It's misleading. Okay. Well, at least there's among the Miserovich parameters, there are certain which have this property. I'm not talking about all of them. Then Lim sup as lambda converges to lambda star of log of the dilatation, real dilatation of C hat lambda is at least the hyperbolic distance between lambda star and m star. So m star is as usual, it's the image under zeta hat of lambda star. Okay? I can put it up. I did not plan on spending too much time on the proof of this, just saying that there's something to do, at least we have to work a little bit. So how can we use this then to push our argument through here? We need to be able to control the hyperbolic distance between a parameter lambda and its image m. And I have to erase something. So let me just redo this picture here. So you have, this is MPQ hat. Everybody in here have an attracting cycle. Actually, it's a fixed point for f lambda. It has a multiplier rho, so there's a natural map from this, call it HPQ hat, onto the unit disk, rho. So rho of lambda is f lambda prime of alpha prime lambda. So alpha prime lambda, I call it the alpha fixed point of f lambda. So it's also a Q cycle for the original polynomial p lambda. It's the one that coalesces with the parabolic fixed point at the root. And this multiplier function actually is univalent on a neighborhood. So it extends univalently at least to some disk of definite size. So I can invert it, and I can take rho here as my parameter. So write lambda of rho instead of rho of lambda. Since it's a univariate map, it makes sense. And then there's a proposition which is also sort of classical. It's mostly the content was conjectured by Mandelbrot, and there was a proof. I forgot who the authors were, but there was this workshop or semester and at Mittag-Leffler in, I don't know if it was 1983, where also the Douady and Hubbard version of Thurston's paper was written, in which they prove something of the style. Yes. That if I take lambda of, say, log of rho, then this is minus log of rho, well, yes, log of rho, over Q minus a number which is actually the residue iterative for the root, for those who know, of log of rho over Q squared plus something where it's of order cubed. Okay? So how can I interpret this as something useful? How does it give me some information on the hyperbolic distance between multipliers? Well, on the unit disk, I mean, if I'm very close to the root here, which corresponds to 1, my map is almost linear. So just to give you a convincing argument, and then you can go home and do the actual, if you want to do the estimates. So I have, you see there's a 1 over Q in the denominator here. So you should think that this disk is reproduced with radius 1 over Q. And if I have 2 of them, I have another disk, maybe 1 over Q prime, and they're not the same. And the correspondence, zeta of lambda gives m. It's actually, if you take on the unit disk, so if you have rho in the unit disk, then zeta applied to lambda of rho is exactly m of rho, because hybrid conjugacies preserves non-repelling multipliers. So I have a picture like this, and what are the points? Well, points like this correspond to the same angle. It actually is like you just take 2 points on the same straight line if they were exact circles. And of course, if they make the slope here become more and more vertical, the hyperbolic distance between points just diverges to infinity. So it's very simple that when you come close to the root, the hyperbolic distance goes off to infinity. Yes?
One circle to the other just by multiplying by q prime over q.
Yes, I do, essentially.
A point and
Pardon?
the distance between a point and the multiplication of. Okay.
Yeah, it's true that you're sort of thinking of what's going out here, and there the distance is bounded, but when you come tangentially, the distance goes off to infinity. So when we were trying to prove that these are actually quasi-conformally homeomorphic, we had a construction and eventually got to look at this, and you know, one day you close your door and you look at the drawing, you say,
Well, that cannot be.
you go back and you look at it, and you see, well, the hyperbolic distance is actually going off to infinity when you approach it tangentially along the boundary here. So corollary. If I look at the hyperbolic distance in H plus between lambda of e to the it and m of e to the it, which of course correspond under this, then this goes to infinity as t tends to 0. You don't look satisfied, Hamill. Yes.
Any number is nice. Any real number is
An isometry.
right halfway.
Yes. And on the
One point appears to me to be just a multiplicity
of the other. So on the chord geodesic, it's just a translation. But when you move away from the chord geodesic being the real line, you're moving more and more.
Just in being on the imaginary axis, you move your point. So.
If you just take 1 over z, then you just get the parallel lines and
Yes.
slide
Yes.
diagonal curves.
Okay. Or you could make the band model, and then if you are the chord geodesic will then be, so band model is like plus and minus I pi. Okay. Chord geodesic being the real line, and circles would be parallel to this. And if you take a circle high up, the translation is very big. Okay? It's surprising, but it's simple. Okay? And then to complete the argument, do I have more time? Okay. We need to move out to Misiorowicz parameters. So let's go back. So on this copy, we have limbs. So a limb has sublimbs. So if I go to a point here, which is, say, e to the I rho equal to e to the I 2 pi r over s.
I thought we had something here. Wait, what did we just show them?
We just showed that the dilatation goes away to infinity on the boundary of the hyperbolic component. And the places where we know to transfer this to parameter space, okay, just to complete.
Transferred back.
But they're dense. So, okay.
Oh, okay, I'm sorry.
So if you, here you have a limb attached. So you just have to use Yoko's inequality to ensure that you have limbs of sufficiently small hyperbolic diameter, well, bounded hyperbolic diameter. And then in that limb, you're going to find, as Xavier says, our parameters lambda star. Okay?
So you're looking at these limbs attached.
Yes.
Going towards the cusp. So can you
Let me just write it.
statement about?
Yeah, I'm going to, yes.
Parabolic points of attachment to those links just as good as your Lyubich parameter.
Oh, maybe it is. It's just that it's related to the alpha fixed point and not the beta fixed point. But you're saying that I should see.
They're also going to have to be taken to each other by your map.
Yes, but how do you? I mean, the control you have in dynamical plane is close to the beta fixed point.
Ah, I see. Okay.
So I don't really know how it distributes. Of course, pre-images of beta fixed point are dense, but how do they accumulate on little?
Okay.
I don't know. So let me say this. So take e.g. Rn over Sn to be n squared minus 1 over n cubed. So essentially this is like 1 over n. So it approaches the root like 1 over n. But Yoko's inequality is going to tell you that you are having a size which is of the order of the denominator, which is size 1 over n cubed. So proposition. There exists C constant depending on P over Q, such that for all n, the hyperbolic diameter of, I should have given this thing a name here. Move the index P over Q up and write R over S. So it's the R over S lim of the principal hyperbolic component HPQ. Then the hyperbolic diameter in H plus of LPQ n squared minus 1 over n cubed go to 0 as n tend to infinity. And then, of course, it's clear that we can take our sequence lambda n star to be in these limbs, and their hyperbolic distance will satisfy well, okay. So proof of theorem, take lambda n star in LPQ n squared minus 1 over n cubed as in, and give it a name here, theorem 2. Then the limit as n tend to infinity of the hyperbolic distance in H plus of lambda n star and theta hat of lambda n star go to infinity as n converges to infinity. And applying then theorem 2, we have proof of our theorem. Is it clear? So I'd like to finish, if I have more time, with a few questions. 2 minutes. So here, for these particular limbs, we have bounded hyperbolic diameter of the limbs. You could ask several questions. Is it true that there is a constant for each hyperbolic component P over Q, so that all limbs have a uniform bounded hyperbolic diameter in the right half plane? So, given P over Q, does there exist CPQ positive such that for all R over S, the hyperbolic diameter in H plus of LPQ R over S is smaller than or equal to C. And you may ask a simpler question. So same question, but restricting to the little copy. So the hyperbolic diameter in H plus of the intersection LPQ R over S with MPQ hat. I suppose I should have been consistent and put hats all over these, but it's too late. Yeah, so does there exist a constant? Okay. Same hypothesis. Blah, 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 blah. Okay. Ah, thank you. That's the problem. It's less than C. So if you think about the Mandelbrot set and you think about Jeremy's talk, where we were seeing these elephants. So they were marching into the cusp of the Mandelbrot set, but there are similar pictures marching into every fjord of every hyperbolic component. So the question is if the antennas of these little copies actually start becoming long to the sides. If you blow this up to become a line, so you have one copy here which has an antenna, and maybe the next in line starts here and it has an antenna, and they grow longer and longer. So we know that they cannot come too close to the other side because we have an external parameter array separating. And it's almost periodic, asymptotically periodic, because we can control it via parabolic implosion. So we know that the problem is not that we are getting too close to the other side. The problem is that they might be growing in this side. We should think that if this is 1 over n, then this is 1 over n plus 1, etc. So the question is, are we able to find a uniform estimate? I'm sure that once you find estimates for these guys, all the other ones who are living here, they will be shielded by the other ones. So each one of these, another question related to this, is that, so a Mandelbrot set comes with a spine. Ah, okay. I just stop here. Sorry.
Quick question.
Could you pinpoint the first place in the argumentation where you used that P over Q is not equal to P prime over Q prime in all the analysis?
Yes. It's when you do the comparison of these two, that you have different radii of the circles. Did I erase it? Here.
So that clearly, I mean, so there's the Q.
There's a Q and there's a Q prime.
Right. Oh, I see. Although the P is worth only finally many P's for a given Q anyway. So.
Yeah.
Wait, but if you have Q over Q and P prime over Q.
Yes.
You have QC or you don't have QC?
Oh, we don't know. And what I'm saying is that in an attempt to try and answer this question, if they're quasi-conformally the same, when you have the same denominator, we have an idea that it might work if we are able to bound the hyperbolic diameters, maybe not of the limbs, but of the sublimbs relative to the little copy.
she doesn't see that the picture.
Yes, yes.
And she doesn't have that complete.
No, exactly. It's, from computer pictures, you cannot see it.
No, but especially if you have low resolution.
Yes.
And he will better like the way.
Pass it again.